Have you ever wondered if the universe is hiding a secret in plain sight? Not inside black holes, not at the edge of the universe, not buried beneath mountains or locked inside distant galaxies, but inside two tiny particles, so small that billions of them could pass through your body every second without you ever noticing. Imagine this. Two particles are born together in the same instant. For a brief moment, they share a common history. Then they are pulled apart. One remains here on Earth. The other begins an impossible journey. Beyond the moon, past the planets, across the darkness between stars, farther than any spacecraft has ever traveled. Now imagine waiting years before touching either one. The moment you finally measure the particle in your hand, something remarkable happens. The distant particle suddenly seems to know what you discovered. Not a second later, not after a signal crosses space. Its connection appears to have existed all along. For nearly a century, this strange behavior has challenged the smartest minds on Earth. It made one of history's greatest physicists deeply uncomfortable. Albert Einstein called it spooky action at a distance. He believed nature could not possibly work this way. Surely something was missing. Surely there had to be a deeper explanation. But every experiment performed since then has only made the mystery stronger. Today, physicists can create these strange connections in laboratories. They send entangled particles through optical fibers beneath cities. They bounce them off satellites orbiting Earth. They use them to build machines unlike anything humanity has ever created. Yet despite all this progress, no one truly agrees on what quantum entanglement is trying to tell us. Is it simply an unusual feature of tiny particles? Or is it revealing something much bigger? Something about space itself, about information, about reality, perhaps even about the universe. Tonight, we are not just exploring one of the strangest discoveries in physics. We are following a trail that begins with tiny particles and may end by changing everything we think we know about existence. Because the greatest mystery of quantum entanglement is not that two particles remain connected. The greatest mystery is why reality allows such a connection to exist at all. Long before scientists had ever heard the word quantum, the universe appeared wonderfully predictable. If you threw a stone, you could calculate where it would land. If you knew the position of every planet, you could predict an eclipse centuries into the future. The moon followed its orbit, the tides followed the moon. Apples fell toward Earth. Everything seemed connected by clear and understandable laws. This view of nature became one of humanity's greatest triumphs. In the late 17th century, Isaac Newton showed that the same force pulling an apple toward the ground also guided the moon around Earth and the planets around the sun. For the first time, the heavens and Earth obeyed one set of mathematical rules. It was a breathtaking idea. The universe behaved like a giant clock. Every gear influenced another. Every event had a cause. Every cause produced an effect. If you knew enough about the present, you could predict the future. This confidence became even stronger during the 18th and 19th centuries. Scientists discovered electricity, magnetism, heat, light, chemical reactions. Again and again, nature rewarded careful observation with elegant laws. Then came one of the greatest achievements in physics. James Clerk Maxwell united electricity and magnetism into a single theory. His equations predicted that light itself was an electromagnetic wave. A beam of sunlight, a radio signal, an X-ray. All were different expressions of the same invisible field. It was another reminder that nature preferred unity over chaos. Many physicists began to believe they were approaching the end of discovery. Perhaps only a few details remained. Perhaps the universe had almost given up all its secrets. There is a famous story, although historians debate its exact wording. Near the end of the 19th century, some scientists believed physics was nearly complete. Future generations, they thought, would simply make more precise measurements. The great adventure seemed almost over. But nature prepared a surprise. Actually, several surprises. The first hints appeared in places no one expected. Hot pieces of metal, electric sparks, the color of glowing objects, small laboratory experiments that refused to obey the beautiful rules everyone trusted. One puzzle involved something as ordinary as heat. Place a piece of iron inside a fire. At first it glows dark red, then orange, then yellow, eventually almost white. Scientists wanted to calculate exactly how much light a hot object should emit at every color. The equations looked straightforward, yet every calculation ended in disaster. The mathematics predicted something impossible. According to classical physics, a hot object should release an infinite amount of ultraviolet light. Infinite, not merely a large number. Infinity. Clearly, that could not happen. No furnace exploded with infinite energy. No candle emitted endless radiation. Nature disagreed with the equations. In 1900, a German physicist named Max Planck made a desperate mathematical assumption. He suggested energy was not emitted continuously. Instead, it came in tiny packets, little bundles, small, indivisible pieces. He did not believe this idea described reality. He considered it a temporary solution. But the trick worked. Perfectly. The impossible infinity disappeared. Without realizing it, Planck had opened the door to an entirely new universe. Today, we call those tiny packets quanta. That single word eventually gave birth to quantum physics. At first, almost nobody understood how revolutionary this idea would become. Planck himself certainly did not. He believed someone else would eventually discover a more comfortable explanation. Instead, the opposite happened. The deeper scientists looked, the stranger reality became. Only 5 years later, a young patent clerk in Switzerland began studying another mystery: light itself. For centuries, light had behaved like a wave. It bent around corners. It created interference patterns. Two beams could combine into bright and dark stripes. Every experiment supported the wave picture. Then another puzzle appeared. When light struck certain metals, it knocked electrons free. This became known as the photoelectric effect. The strange part wasn't that electrons escaped. The strange part was how they escaped. Brighter light should have carried more energy, at least according to classical theory. But experiments showed something unexpected. Blue light, even when dim, could eject electrons. Red light, no matter how intense, often could not. It was as though color mattered more than brightness. No one could explain why. Albert Einstein proposed a shocking answer. Perhaps light was not only a wave. Perhaps it also behaved as tiny particles. Each carried one packet of energy. Today, we call these particles photons. If a photon lacked enough energy, increasing the brightness simply produced more weak photons. It never solved the problem. Only photons above a certain energy could free an electron. Suddenly, the experiments made sense. Einstein's explanation was revolutionary. Ironically, this work, not relativity, earned him the 1921 Nobel Prize in Physics. References: Albert Einstein, On a Heuristic Point of View Concerning the Production and Transformation of Light, 1905. Nobel Prize in Physics, 1921. But this solution created an even deeper mystery. How could light be both a wave and a particle? Those ideas seemed impossible to combine. Imagine throwing a pebble into a lake. The pebble is one object. The ripples are spread everywhere. Now imagine something that is somehow both, localized and spread out, a particle and a wave. Nature seemed perfectly comfortable with this contradiction. Human intuition was not. For thousands of years, our brains evolved to understand stones, trees, rain, animals. None of those prepared us for the microscopic world. The closer scientists looked, the less reality resembled common sense. And then, the electrons themselves began behaving in ways that no one could explain. The electron was supposed to be one of the simplest things in nature. It carried a fixed amount of electric charge, it had a tiny mass, it moved around the nucleus of an atom. Nothing about it seemed mysterious. At least, that was the expectation. But whenever scientists tried to observe electrons carefully, they found themselves trapped inside a puzzle that refused to disappear. Imagine standing beside a calm lake just before sunrise. The surface is perfectly still. You throw 2 small stones into the water. Circular ripples spread outward. Eventually they meet. Where one crest meets another crest, the water rises even higher. Where a crest meets a valley, they cancel each other out. Beautiful patterns appear naturally. No single ripple decides where to go. The entire wave spreads through the lake at once. This behavior is so familiar that we rarely stop to admire it. Waves interfere. That is simply what waves do. Now imagine replacing those ripples with tiny bullets fired from a gun. Each bullet chooses one path, one destination, one impact. Bullets do not spread across a lake. They cannot travel around 2 different rocks simultaneously. They certainly do not interfere with themselves. Or at least, that is what common sense insists. For centuries, nature seemed to agree. Large objects behaved like particles, water behaved like waves. The distinction appeared absolute. Then someone asked an innocent question. What would happen if electrons were fired toward a wall containing 2 tiny openings? No one expected the answer to change physics forever. At first, the experiment sounded almost childish. A source releases electrons. Ahead is a barrier. The barrier contains 2 narrow slits. Behind it sits a screen that records where every electron arrives. If electrons behave like tiny balls, the result is obvious. Some pass through the left slit, others pass through the right. The screen should display 2 bright bands. Nothing more, nothing less. That prediction seemed so certain that no one would have doubted it. Then the experiment was performed. The screen did not show 2 bands. Instead, it revealed dozens of alternating bright and dark stripes, exactly the kind of pattern created by overlapping waves. Scientists checked their equipment, again and again. The result remained. Electrons somehow behaved like waves. But perhaps, someone argued, the electrons were simply colliding with one another. Maybe millions of electrons together created this strange pattern. So the experiment became even more careful. The source was weakened. Instead of releasing millions of electrons, it released one, a single electron, then another, then another. Sometimes several seconds passed between each one. Only one electron existed inside the apparatus at any given moment. Surely now the mystery would disappear. There were no neighboring electrons to interfere with. Each electron traveled completely alone. Each should choose either the left slit or the right slit. Nothing else seemed possible. Hours passed. Thousands of individual electrons slowly struck the screen. Each arrived as a tiny point, one dot, then another, then another. If you watched in real time, nothing looked unusual. But as more dots accumulated, something astonishing emerged. The same interference pattern appeared again. The pattern built itself, one electron at a time. It was as though every electron somehow interfered with itself. Pause for a moment and think about what that means. One object, one electron, one arrival. Yet its behavior could only be explained if something wave-like had passed through both slits. How can one thing travel through two different openings? Not half through one, half through the other. The mathematics suggested something even stranger. Before the electron was detected, its possible paths existed together as one combined description. The electron was not following a hidden route we simply failed to observe. Instead, quantum theory described every allowed possibility evolving together. This idea became known as superposition. It is one of the most misunderstood ideas in all of science. Superposition does not mean an electron is physically duplicated like identical twins. It does not mean there are two little electrons secretly flying around. Instead, the quantum state contains multiple possible outcomes simultaneously. As long as no measurement forces a definite result, those possibilities continue to evolve together. That sentence sounds simple. Its consequences are anything but. Because if superposition is real, then nature is doing calculations unlike anything we experience in ordinary life. Every possible path contributes. Every allowed history matters. Richard Feynman, one of the 20th century's greatest physicists, later developed a powerful way to calculate quantum behavior. He imagined particles exploring every possible path between 2 points, not because tiny particles consciously make decisions, but because the mathematics works exactly as if every path contributes to the final answer. Some possibilities strengthen one another. Others cancel out completely. Only after adding them all together does reality reveal the outcome we observe. Feynman once remarked that the double-slit experiment contains the only mystery of quantum mechanics, not the only strange feature, the only mystery. Because if you truly understand why the double-slit experiment behaves this way, you understand why quantum physics had to replace classical physics. And yet, even today, no one can honestly say they fully understand why nature behaves this way. Naturally, scientists became curious. Perhaps the electron really was choosing one slit. Maybe the interference pattern appeared because we simply lacked enough information. There was an obvious solution. Watch it. Place a detector beside each slit. Observe which opening the electron actually uses. Once we know its path, the mystery should disappear. The experiment was rebuilt. Tiny detectors were positioned near the slits, sensitive enough to reveal the electron's route. The electron approached. The detector waited. And this time, the electron chose one slit, exactly as common sense predicted. Problem solved? Not even close. Because something else vanished, the interference pattern. The beautiful alternating bands disappeared completely. Only 2 ordinary bands remained, as though the electron had suddenly remembered how classical particles are supposed to behave. Scientists repeated the experiment countless times. Different detectors, different materials, different techniques. The conclusion never changed. Whenever nature allowed the 2 paths to remain indistinguishable, interference appeared. Whenever the path became knowable, interference vanished. Notice something extraordinary. The detector did not need a human being standing beside it. The universe did not wait for someone's eyes. What mattered was that information about the path became available in principle. This point has often been misunderstood in popular culture. People sometimes hear the phrase, "the observer changes reality," and imagine consciousness magically controlling the quantum world. Modern physics does not require that interpretation. In standard quantum mechanics, an observation is a physical interaction, a photon scattering from an electron, an atom colliding with another atom, a detector recording information. The mystery is not that human minds possess supernatural powers. The mystery is deeper. Why does obtaining information change the mathematical description of reality itself? That question remains one of the central puzzles of quantum mechanics.
And as physicists continued asking it, they stumbled upon an even stranger discovery. It turned out that two particles could share a single quantum state.
Not because they remained physically connected by an invisible string, not because they secretly exchanged signals, but because quantum theory sometimes refused to describe them separately at all. And that idea would eventually become known as quantum entanglement. It sounded almost impossible, but compared to what came next, everything you have heard so far was only the beginning. For centuries, science had followed a comforting pattern. Observe nature, find a rule, write an equation, predict the future. Again and again, the universe rewarded this approach. Every mystery eventually became another solved chapter in a growing book. Gravity explained the falling apple. Maxwell explained light. Thermodynamics explained heat. Each success strengthened a quiet belief. The universe might be strange, but underneath its complexity, it was understandable. Then quantum mechanics arrived, and something unusual happened. The equations worked beautifully, more accurately than any theory before them. Yet the meaning of those equations became harder to explain with every passing year. Usually in science, mathematics is the difficult part. The physical picture comes later. Quantum mechanics reversed that order. The mathematics became astonishingly successful. The picture of reality became increasingly mysterious. Physicists could calculate the behavior of atoms with extraordinary precision. They could predict the colors emitted by hydrogen, the stability of matter, chemical bonds, the operation of lasers, semiconductors, magnetic resonance imaging. Every modern electronic device quietly depends on quantum mechanics. Without it, the world around you would look completely different. Your smartphone would not exist. Modern computers would not exist. GPS systems would fail. The internet itself would struggle to function. Quantum mechanics is not an obscure theory locked inside universities. It is woven into almost every technology that defines modern civilization. And yet, ask a room filled with physicists one simple question: what is actually happening? You may receive 10 different answers. That is extraordinary. Imagine asking engineers why airplanes fly and hearing completely different explanations from each one. Imagine surgeons disagreeing about whether blood even exists. In every mature science, there is usually broad agreement about what the equations describe. Quantum mechanics is different. The predictions are nearly perfect. The interpretation remains unsettled. That is why the famous quote by Richard Feynman still echoes through physics. I think I can safely say that nobody understands quantum mechanics. Notice what he did not say. He did not say nobody can calculate quantum mechanics. He did not say the theory is incorrect. He meant something far more unsettling. Nobody truly understands why reality behaves this way. Tinker again about the lonely electron approaching the two slits. Before it reaches the barrier, quantum mechanics does not assign it one definite path. Instead, it describes a mathematical object called the wave function. This word appears constantly in quantum physics, yet it is often introduced so quickly that its mystery is lost. So let us slow down. Imagine standing on top of a mountain during heavy fog. Below you lies an enormous valley. Somewhere inside that fog is a single traveler. You cannot see where they are, but you know something. Certain regions are more likely than others. Perhaps there is a road winding through the valley. Perhaps steep cliffs make other regions unlikely. You begin drawing a map, not showing where the traveler is, but showing the probability of finding them. High probability here, low probability there, 0 probability beyond the cliffs. At first glance, the wave function seems similar, but there is a crucial difference. The fog map represents your ignorance. The traveler always occupies one actual location. You simply do not know it. Quantum mechanics refuses to make that assumption. The wave function is not merely a map of missing information. At least, not according to the standard interpretation developed during the 1920s. Instead, the wave function itself evolves according to precise mathematical laws. Every possible outcome contributes. Every possibility interferes. Every possibility influences the final probabilities. The wave function is not simply describing uncertainty, it becomes part of the theory itself. This distinction is easy to miss, yet it changes everything. Suppose you flip an ordinary coin. Before looking, you do not know whether it landed heads or tails. Your uncertainty exists only in your mind. The coin itself already knows. Lift your hand, the answer has been waiting all along. Quantum systems behave differently. Before measurement, the theory does not assign a hidden answer in the same way. Instead, it evolves a collection of possibilities. That statement made many physicists deeply uncomfortable, including Einstein, because Einstein believed nature should possess definite properties whether anyone measured them or not. The moon surely does not cease to exist simply because no one is looking. He once joked, "Do you really believe the moon exists only when you look at it?" It was not merely a joke, it was a challenge. If quantum mechanics says reality itself lacks definite properties before measurement, then perhaps quantum mechanics is incomplete. Perhaps something deeper remains hidden beneath the equations. This became one of the greatest scientific debates of the 20th century, not about mathematics, about reality. What kind of universe do we actually live inside? One where properties exist independently of observation, or one where reality itself is somehow less definite than we have always imagined? Notice how radically different these possibilities are. The first preserves common sense. The second asks us to abandon ideas that have guided human thinking for thousands of years. Neither option feels comfortable, and that's precisely why the debate refused to disappear. Then another mystery emerged. It began with a simple question. If one particle can exist in a superposition, can two particles share the same superposition? The equations answered immediately. Yes. Not only can they share one, sometimes they cannot even be described independently anymore. Imagine two dancers beginning a performance. At first, they stand together. Every movement is perfectly coordinated. Then the stage slowly separates. One dancer moves to the left, the other to the right. Eventually, they stand on opposite sides of an enormous theater. You can still describe each dancer individually. One has raised an arm, the other has turned slightly. Each possesses their own independent position. Now imagine something stranger. Imagine trying to describe one dancer and discovering it is impossible. Every sentence about the first dancer is incomplete until you also describe the second. It is not merely that they remain synchronized, their identities have become mathematically linked. One description, shared by both. This analogy is still imperfect, because real dancers always possess independent existence. Quantum particles sometimes do not. Their wave functions merge into one mathematical object. The system becomes the fundamental reality. The individual particles become secondary. Pause there, because this is where quantum entanglement quietly enters the story. Most popular explanations say two particles become connected. That picture is useful, but it is also misleading. It makes us imagine invisible ropes stretching across space. Quantum theory says nothing about ropes, nothing about hidden cables, nothing about secret radio signals. Instead, the mathematics simply refuses to separate the particles into independent descriptions. There is only one quantum state, shared across both. As long as that shared state survives, the particles behave as parts of one quantum system, even if space itself tries to pull them apart. And now, a new question appears. A question so disturbing that Einstein himself could not accept the answer. If these particles no longer possess completely independent descriptions, then what happens when they are separated by millions of kilometers? The equations gave an answer. Einstein called it impossible. The experiments had not yet spoken, but they soon would, and when they did, The mystery of quantum entanglement would become far stranger than anyone had imagined. Imagine that you were holding two perfectly ordinary gloves. One is made for the left hand, the other for the right. You place each glove into a separate box. Without looking, you send one box to New York. The other travels to Tokyo. Months later, someone in New York opens their box. Inside is the left glove. At that exact moment, they instantly know something about the unopened box in Tokyo. It must contain the right glove. Nothing mysterious has happened. No message traveled between the boxes. The gloves already possessed their identities before either box was opened. The observer merely discovered information that had existed from the beginning. This kind of correlation is completely familiar. Every day, our brains make predictions like this. If you find one sock, you know where its partner belongs. If you see one side of a coin, you immediately know the other side. Information spreads inside your mind. Reality itself does not change. Einstein believed quantum mechanics should work in the same way. Perhaps quantum particles only appeared mysterious because we lacked complete information. Perhaps each particle secretly carried hidden instructions from the instant they were created. Imagine two tiny envelopes. Inside each envelope is a complete script, not just for one experiment, but for every possible experiment anyone could ever perform. The particles never need to communicate. They never need to exchange signals. When measured, they simply reveal the answers they have been carrying all along. This idea became known as hidden variables. The name sounds technical. The idea is remarkably simple. Quantum mechanics, according to Einstein, might resemble reading only the final page of a novel. You can predict many things, but you are missing the earlier chapters. The missing chapters, the hidden variables, would restore certainty to the universe. Reality would once again become complete, predictable, objective, independent of observation. To Einstein, this was not merely a preference, it was almost a philosophical necessity. He had spent his life uncovering deep order beneath apparent complexity. Special relativity revealed that space and time were not separate. General relativity showed that gravity was geometry itself. Again and again, nature rewarded the search for deeper explanations. Why should quantum mechanics suddenly abandon that tradition? In 1935, Einstein joined two colleagues, Boris Podolsky and Nathan Wren, to publish one of the most influential papers in the history of physics. Today, it is known simply as the EPR paper. Its title was surprisingly modest. Can quantum mechanical description of physical reality be considered complete? Notice the wording. They were not claiming quantum mechanics was wrong. In fact, they fully accepted its astonishing predictive success. Instead, they questioned something deeper. Was the theory telling the whole story, or only part of it? The EPR argument begins with an idea that sounds almost impossible to disagree with. Suppose you can predict something with absolute certainty, without physically disturbing the object. Then surely that property already existed. It was already real. Otherwise, what exactly are you predicting? Imagine watching a solar eclipse. Astronomers can calculate the exact moment the moon covers the sun, years before it happens. They are not creating the eclipse through observation. They are predicting something that will exist regardless of who watches. Einstein believed quantum measurements should work the same way. If measuring one particle allows you to predict another perfectly, then the second particle must already possess the corresponding property. Nothing mystical, nothing instantaneous, just hidden information. At first glance, this reasoning feels almost unavoidable. Many people encountering quantum mechanics for the first time instinctively agree with Einstein. Perhaps the theory is incomplete. Perhaps one day someone will discover the deeper mechanism underneath. And for nearly 30 years, that possibility remained alive. No experiment could distinguish between Einstein's picture and the standard quantum picture. Both made the same observable predictions.
The debate seemed trapped inside philosophy. Some physicists even dismissed it as unanswerable. After all, how could anyone experimentally test something hidden? Then, in Northern Ireland, the young physicist named John Stuart Bell began thinking about Einstein's argument. Bell admired Einstein deeply. He also respected quantum mechanics. Rather than choosing sides, he asked a different question. Suppose hidden variables really exist. Suppose every particle carries hidden instructions exactly as Einstein imagined. What consequences would follow? Not philosophical consequences, mathematical ones. Bell realized something extraordinary. Any theory based on local hidden variables, that is, hidden instructions combined with the idea that influences cannot travel faster than light, must satisfy certain numerical limits. These limits are now called Bell inequalities. The equations themselves are not especially complicated. The idea behind them is. Imagine giving two students identical instruction sheets before they enter separate examination rooms. Once inside, they cannot communicate. Every answer they give must originate from the information they carried with them. No matter how clever those instructions are, there is a maximum level of agreement they can achieve. Bell discovered that Einstein's universe also has such a maximum. If hidden variables really exist, certain correlations can never become stronger than a specific limit. Quantum mechanics predicted something astonishingly different. It predicted that entangled particles could violate Bell's inequality. Not slightly, systematically. If experiments observed those stronger correlations, then hidden variables could not explain nature. Notice what Bell had accomplished. For decades, people believed the debate between Einstein and quantum mechanics belonged to philosophy. Bell transformed it into experimental science. For the first time, reality itself could choose a side. Reference: John S. Bell, on the Einstein-Podolsky-Rosen paradox. Physics, Volume 1, 1964. The challenge now became enormous. The effects Bell predicted were incredibly subtle. Tiny imperfections could easily hide the answer. Experimental physicists spent years developing instruments precise enough to perform the test. Among the pioneers was John Clauser. His team performed some of the first Bell tests during the early 1970s. The results were intriguing. Again and again, nature leaned towards quantum mechanics. But skeptics remained unconvinced. Perhaps the detectors missed certain particles. Perhaps hidden variables still survived inside unnoticed loopholes. The experiments became more sophisticated, more precise, more demanding. Then came the work of Alain Aspect in the early 1980s. Aspect realized something clever. Suppose the particles somehow knew in advance which measurements the scientists planned to perform. Could hidden variables exploit that knowledge? To prevent this, Aspect rapidly changed the measurement settings while the particles were already traveling. The particles had no opportunity to adjust beforehand. The outcome was stunning. Quantum mechanics won again. The correlations exceeded Bell's limit, exactly as the theory predicted.
Years passed. Technology improved. Lasers became more stable. Detectors became faster. Experiments stretched across longer and longer distances. Physicists closed loophole after loophole. Some tests separated the detectors by kilometers. Others used random number generators based on distant starlight to choose measurement settings, making it extraordinarily difficult for any hidden coordination to explain the results. By the 2010s, multiple independent groups had performed what are known as loophole-free Bell tests. These experiments closed the major experimental loopholes simultaneously and continued to support the predictions of quantum mechanics. In recognition of this work, the 2022 Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger.
for experiments with entangled photons that established the violation of Bell inequalities and paved the way for quantum information science. Think about what this means. Einstein's intuition was not foolish. It was one of the most carefully reasoned arguments ever made in physics. For decades, many brilliant scientists expected nature to agree with him. Instead, experiment after experiment sided with the stranger picture. But here's the part that is often misunderstood. Bell's experiments did not prove that information travels faster than light. They did not show that physicists can send messages instantaneously across the universe. In fact, special relativity remains completely intact. No secret communication channel has been discovered. So then, what exactly is happening? If nothing travels between the particles and hidden local instructions cannot explain the correlations, what is the universe doing? That question is where the real mystery begins, because Bell did not tell us what entanglement is, he only told us what it cannot be. And sometimes, knowing what reality cannot be is even more unsettling than knowing what it is.
The laboratory was silent. A pair of photons had just been created. For less than a billionth of a second, they existed together. Then mirrors redirected them. One traveled left, the other right. The distance between them grew. A few centimeters, a few meters, hundreds of meters. Eventually, kilometers. Everything about our everyday experience tells us that increasing distance weakens relationships. Friends drift apart, voices become quieter. Gravity weakens. Magnetic fields fade. Light grows dimmer. Distance usually means less connection. Nature has taught us this lesson our entire lives. So when physicists separated entangled particles farther and farther apart, they expected one possibility. If some unknown interaction connected them, that interaction should eventually weaken, like a stretched rubber band, like a fading radio signal, like every force we already knew. But something unexpected happened. The mathematics never included weakening, and neither did the experiments. Whether the particles were 1 meter apart or 1,000 kilometers apart, the correlations remained exactly as quantum mechanics predicted. Not approximately, exactly. It was almost as if distance itself simply wasn't part of the relationship. Pause there, because this is the moment where our everyday intuition quietly begins to fail. We instinctively imagine two particles as two separate objects, one here, one there, separated by empty space. Quantum mechanics asks us to consider a completely different picture. Perhaps the particles are not truly two independent things anymore. Perhaps the entangled state itself is the fundamental object, and what we call two particles are simply two places where that single quantum state can be observed. This sounds abstract, so let us slow down. Imagine reading a novel. The first half is printed in one book, the second half is printed in another. You place the books in different cities. Have you separated the story? Not really. You have separated the paper. The story still exists as one complete object. Neither book contains the whole narrative. Only together do they make sense. Entanglement is not exactly like this, but it points towards something important. Sometimes the relationship contains more reality than the individual objects. That idea appears again and again throughout modern physics, not just in quantum mechanics, in thermodynamics, in information theory, even in attempts to understand gravity itself. The relationships may be more fundamental than the things being related. For centuries, science focused on objects, planets, atoms, electrons, particles. Quantum physics slowly shifted the focus. Sometimes the connections are what matter most. And this leads us to one of the most profound ideas in all of quantum theory: information. Most of us think of information as something humans create. Books contain information.
Computers store information. Your phone holds photographs, messages, and videos. But modern physics treats information differently. Information is not merely something we write down. It is something nature itself possesses. Every physical system contains information. The spin of an electron, the polarization of a photon, the position of an atom. Nature is constantly carrying information. In fact, some physicists believe information is even more fundamental than matter. That sentence sounds almost unbelievable. How can information exist before physical objects? Yet over the last 50 years, again and again, physics has pointed in that direction. John Archibald Wheeler, one of the most influential physicists of the 20th century, proposed an extraordinary phrase: "It from bit." Only 3 words, yet they contain an astonishing possibility. Every particle, every field, every force, perhaps every object in the universe, could ultimately arise from information. Not everyone agrees with Wheeler's idea, but it has profoundly influenced modern theoretical physics. If Wheeler was even partly correct, then entanglement becomes much more than a curious property of particles. It becomes a relationship between pieces of information. And suddenly, the mystery becomes far larger than electrons and photons. Now consider something else. Imagine 2 ordinary coins. You flip them independently. Each has a 50% chance of landing heads. Knowing one coin tells you almost nothing about the other. They are independent. Now imagine they are magically linked. Whenever one lands heads, the other always lands tails. You have gained information. The 2 coins no longer behave independently. Their outcomes are correlated. Entanglement also creates correlations, but correlations unlike anything found in classical physics. Because Bell's experiments showed these correlations cannot be explained by ordinary hidden instructions. They are stronger than classical reality allows. Physicists sometimes call them non-classical correlations. That phrase sounds technical. Its meaning is astonishing. Nature permits relationships that classical reality cannot produce. Notice what has quietly happened. When we first began this journey, the mystery seemed to concern particles. Now, the mystery concerns information itself. How does nature organize information? Why does information obey quantum rules instead of classical ones? And perhaps the deepest question of all, is information more fundamental than space? That may sound impossible until you realize some of the world's leading physicists are asking exactly that question. For centuries, space was treated as the stage on which physics happened. Planets moved through space. Light traveled through space. Galaxies drifted through space. Space came first. Everything else happened inside it. Quantum entanglement suggests another possibility. Perhaps space is not the stage. Perhaps space is part of the performance. Imagine a giant fishing net.
At first glance, the empty holes seem to define the net, but look more carefully. The holes exist only because the threads connect. Remove every thread, the holes disappear. Perhaps space-time behaves in a similar way. Perhaps what we call space emerges from deeper quantum connections. This sounds almost like science fiction, yet over the past 2 decades, an increasing number of physicists have explored exactly this possibility. One clue comes from something called entanglement entropy. The name is intimidating. The idea is surprisingly beautiful. Entropy usually measures uncertainty or disorder, but entanglement entropy measures something different. It measures how strongly one part of a quantum system depends on another. Imagine tearing a photograph in half. Each piece appears incomplete. Only together do they reconstruct the full image. Entanglement entropy tells us, in a mathematical sense, how incomplete one region of reality becomes when separated from another.
That idea has become incredibly important, not because it explains one experiment, but because it unexpectedly appears in many completely different areas of physics. Quantum computers, condensed matter, black holes, string theory, even attempts to understand the origin of space-time itself. Whenever physicists push toward the deepest questions, entanglement seems to be waiting for them, almost like a familiar face appearing in places where it shouldn't. And that coincidence has made many researchers wonder, what if it isn't a coincidence at all? What if entanglement is not one feature of the universe? What if it is one of the ingredients from which the universe itself is built? That idea would have sounded absurd a century ago. Today, it is the subject of serious research. No one knows whether it is correct, but the fact that respected physicists are willing to consider it tells us something remarkable. We are no longer asking, why are two particles connected? We are beginning to ask, could those connections be creating the reality we experience? If that question sounds impossible, the next mystery is even stranger. Because entanglement does not only challenge our understanding of space, some experiments seem to challenge our deepest intuition about time itself. And when physicists followed that trail, they found themselves confronting one of the most astonishing experiments ever performed in the history of science.